Thank you, Erin. Well, once again, welcome. Uh, this is not going to be a lot of introduction because I don't have to introduce almost anything on Koopman operator theory to anybody in this room, which is really pleasant. So I really want to go through three topics today. One is related to control theory. There is a very interesting rise in the control theory papers and analysis with Carl, who is here. We just put together a little survey of some of the results on performance guarantees. But I will talk about a mathematical aspect of this that I think also needs to be kind of cleared up. As I said, there are questions to be answered, not just things to be proposed. Then I'll talk about what is called a static Koopman operator. So I believe nobody actually in this room saw me speak about either of these topics. So this is new for me as well. It's the first one. It's an idea that says if you have two different spaces, you can still have composition type operators between them. I think it might be a useful thing. And then I'll have an application that is used in AI in general in training of neural nets. A Koopman operator for neural nets that we've did over the last few years. But before I do that, maybe I'll show you something. This is a picture of a particular map. It's a pendulum kicked by periodic forcing, and so on the horizontal is the position, and on the vertical is the momentum. For those of you in dynamical systems, this is called the standard map. And we tried to do the visualization of the state space of this standard map with a method that I based on the Koopman operator way back in my thesis. So this is a result from about 93 as a theorem. We published it as a visualization method in 98, and this is the picture. And this took a student a good 6 months or something like that. So 2010, this is Zoran Lunaic doing his master's at UCSB, and now you're seeing these beautiful, complicated structures that are being discovered using eigenfunctions of the Koopman operator. This is a very complicated map. It has chaotic dynamics in between these islands. So it has period 2 motions, period 3 motions, period 5, whatever period you have. This is ChatGPT, 10 minutes of prompting just by saying, give me the ergodic partition of the standard map. That's me 3 days ago. Prompting ChatGPT for 10 minutes. So, we are working within the context of a super fast advancing field. I mean, arguably that's pretty amazing on the right with the amount of detail that is in there. So I just wanted to show you this. Where do we stand as a status? This is a graph that was collected by someone at AIMDyn. I think it was Alan Avila. And this is the number of publications in the Koopman operator theory between sometimes in 2002 and today. And you're seeing a very clear, very, very clear exponential increase. So interestingly, we are a relatively small part. There is 30 of us here, and that's a much bigger meeting. That's quite a bigger meeting than we had in Toronto last year. But we're actually a relatively small part of that global community that's happening. I'm really amazed by the number of different applications that are going on. Like there are already reviews on vehicular applications of automotive. On the right, modeling and control of soft robotics, the kind of work that a number of that Erwin does and a number of other people have pursued, and then neuroscience, Will is pursuing some of these ideas there. Okay, so this is a slide that I'm going to go through in 30 seconds. The Koopman operator is the composition operator. You all know the history, I hope. Koopman invented it in 1931 to get a connection of classical mechanics with quantum mechanics. Karleman followed in 31 with Karleman linearization. Koopman and von Neumann continued this work in ergodic theory, and then Mori and Zwanzig pursued it in chemical physics. I'm putting it up there so that we realize that we are standing on some, pretty amazing shoulders. Those are spectacular names in the history. This is the fluid flow that we did in 2009. So we were capable of extracting some structures out of this quite complicated chaotic flow, and perhaps that caused quite a bit of interest. Once again, in the vector field case, we have x dot is equal to f of x. If we find the eigenfunctions, that's a good thing. Level sets of eigenfunctions give us the state space structures. And then if we project the states on the eigenfunctions, we get these modes, so spatial structures. So quite useful from both of these perspectives in the context of systems that don't have the control term to it. So the control term itself in this particular context is open loop. And so I can put any space of inputs in a certain space of inputs there. But I'd like to talk a little bit about exactly what kind of an extension, just very theoretically. There is quite a bit of amazing work, and we are going to hear about it quite a bit here, going on design side. So how do we represent systems? But there is also fundamental work that I think needs to be done in the context of what are the spaces we are working in. I just gave a talk in Zagreb, and I spoke about functional spaces for the nominal systems, not for the control systems. It's an interesting question when you have the next state to be a function of the state itself and an external control input as to how to even represent this, because the control input U is not subject to any dynamics to start with, right? It's completely open. This is an open loop setting. If you close the loop, then it's a function of X. So we proposed, so Milan Korda and myself proposed in this paper in 2018, I think, to extend the system so that you have a skew product between the state and the space of controls. But what is your state of controls? Well, you can take it as the space of all possible sequences of inputs. Let's say that the only inputs that you have are 0 and 1. So you have no input or you have an input. Then all possible sequences of zeros and ones, that's your state space. And you do have dynamics on it. You do the left shift. You basically have a sequence of zeros and ones, and now you have a 0, and there is a 1 next to it. So in the next time, you just shift it to the left, and that's your next input, right? So there is a dynamical system associated with this. It's this. And then there is a Koopman operator on this product space. And so you have a functional space on X, and you have a functional space on the space of sequences, and you have a perfectly fine Koopman operator that we are going to call K infinity. This is joint work with Jorge Cortes and Mezic Hasseli. It's going to be at the CDC in Rio, sort of coming up. So if you do it this way, you can recover the trajectory of the system. That's the first little lemma that says, okay, take your T infinity, which is this extended dynamical system on the space and control, iterate it K times, and then project from the product space to the state space itself. And if you start with some x0 and you have the control sequence U as your initial condition, it's a little bit mind-bending to think about the fact that you have an initial condition that is a control sequence. But anyhow, you get the correct trajectories out. Now, there's another approach. You can say, let me fix the input U star at any given time, no sequences. And now I have a family of maps, TU star. And now again, you start from some x0, you apply a sequence of maps, and you're going to get your kth state. So state at time k. And now you can define the Koopman control family. This is what Jorge Cortes and Mezic Hasseli did. I think they were the first one. If I'm wrong, then correct me. And now you have functions in the space F. Remember the previous formulation that was also exact had functions in this F infinity, which is a product space. Yeah? So nicely, if you take an observable F on the state space, you can recover the value of the observable at the kth time by just applying the Koopman operator k times to the initial value of the function, and you get the result. Right? So correctly with this Koopman family, but the Koopman family is very, very large. It's parameterized by all the possible inputs. So these are the two approaches. You also have some naive approaches that don't quite work mathematically. So these are the two that are actually precisely defined. You could say, well, I have a function of x, and I can just take this mapping here, but now I get a function of x and u. So I started with a function of state space, but the next thing up is the function that is on both state space and input space. So that's a problem, because in one step you ran out of the functional space. And functional spaces are important. So the question of how these things work together is kind of an interesting one. And that's what we set out to do. So we asked 3 questions. How can one encode the state information in value of functions in F infinity? That's the product space. So that's one. So similar results to the previous lemma that I have. Now, if you have F infinity and F, so F is just the space of functions on the state space. Some space that you have defined. Note, I'm not defining a function. I mean, I'm not saying L2. I'm not saying some analytic space of functions. I'm just saying some space of functions. So you have F infinity and F. What are the conditions under which these two approaches are exactly the same? And can you actually formalize what is a rich enough space for this kind of an application? And what is the connection between these theoretical frameworks? If you have K infinity, that's a Koopman operator on the product space, versus you have a Koopman operator family. How do they play together? Ultimately, this has consequences for design, because if you want to represent your dynamical system as x dot is ax plus bu in some embedded space, you need to know exactly on what kind of spaces you're working on, and whether these things are even compatible. So there is this idea that says, well, let's define control-independent functions in F infinity. The control-independent functions is basically the ones that can be split into the product of a function of state and a function of input. But that function of input is just an indicator function of the space of all sequences. Again, slightly mind-bending, but that gives you a kind of a nice starting space, and that's an important one. And we'll denote this by FCI, so constant input. And then the second part is if XK is a trajectory of our control system for initial conditions x0 and this input sequence, then for any G in this constant input space, you get a nice result that if iterate K times G, you get exactly the value of that function at xk. So everything's fine. You get an equivalent of the lemma that I presented before. All right. So now we need to connect these two spaces, F and F infinity, formally. And so basically you can do a domain extension and domain contraction. So if F is a function in the space of functions capital F or calligraphic F, the domain extension basically goes by defining F infinity xu to be f of x for every u. And then domain restrictions is you take a function that is in the constant input space and you just basically say, well, it's a constant input space, right? So I'm just going to restrict it by fixing u star and restricting to x. All right, so the theorem that comes out is here. And here is the critical assumption. We need that F infinity, which is in this space, the tensor product space, is the extension, right? For all F element of F, there is a function F infinity that belongs to this calligraphic F infinity, right? So this space here cannot be, in this sense, poorer than this space over here. Otherwise, there is a problem, and there is no comparison between the two. And then the restriction, this G restriction for any G element at F infinity and any input, that must be in the set of all functions on state space. This is how these two things correspond. And then you have a sequence of theorems that basically tell you all the way down to here that if you apply the extension and then you restrict, you get an involution. So you take a function here, you port it over there, then you restrict, and you get back over here. So that's basically the summary of these general results. And then you can say something about the richness, the cardinality of these spaces under these kinds of assumptions is exactly the same. All right. Now, how do these functions actually play together? So the formal frameworks are actually equivalent with domain restricted to the state space. You have, you start with F infinity, you evolve it with K infinity, which is the tensor product space. You restrict it to chi and U star, and you get the evolution with U star. So Koopman operator family evolution is equal to Koopman operator on the product space evolution. That's the result. That's the result here. And then also, if you evolve F infinity starting from some initial condition with K infinity on the tensor product space, that's exactly the same as evolving it with the Koopman operator family under the two assumptions that I gave you before, that the spaces actually correspond to each other. So these are the formal results. We need them to understand when a control system can have an embedded representation that is either linear or bilinear or neither of those and in a particular case. When F infinity and F are not compatible, then you really don't have a way of having these things play with each other. So these are some kind of fundamental requirements. I'll stop there just for a second and see whether there are any quick questions here. Yes. Yes. So you, in principle, you can, calligraphic F can be L2 or space of analytic functions or anything else. The more serious question is the F infinity itself, because the spaces on the, space of sequences, you need to put some kind of a metric on that particular space. And usually it's that 1/2n metric, right? That cancels things out at infinity. And that's where the complexity kind of comes from. All right. Okay, so I'll switch the topic. I think I have 10 minutes still, right? All right. Oops. So I'll try to go fast. In previous talks, I spoke quite a bit about the topics of representations. And the idea of a representation is turning the idea of embedding on its head. It basically says, let's say that you have a linear operator U that is and a Koopman operator associated with some process, but I don't know the model. Can you actually find the set of mappings F and the set of functions little f, such that if you act with a Koopman operator on this set of functions, you actually, that's equal to acting with a mapping on the same set of functions. We all know a nice linear representation. If we get an eigenfunction, then U phi is lambda phi, and that's just linear, right? But this is a more general idea of a representation. And the representation is faithful if these functions separate different initial conditions. And then finally, you have a nice thing that if you have two different representations, so if you're putting in functions that are time delays versus functions that are sines and cosines, then if they're both faithful, they will have a conjugacy between them, right? So that kind of verifies that this is a well-defined mathematical concept. But here is maybe the point in this talk that I feel is somewhat most interesting from the conceptual side. We can define this on, obviously, for dynamical systems when we have a mapping from M to M. But what if you have just a static map from M to N? So all of machine learning and AI says, I'm going to represent Y as some set of constants, some sum of constants times features of X, right? This is all of it. Large language models are all autoregressive. This is what they do. Think about it in Koopman terms. Why not lift on Y? Why not featureize Y? If you're feeling that I'm questioning the whole setup of machine learning as we know it, I am. It doesn't make any sense from the Koopman perspective that you're trying to represent only Y as the set of features of X when you should be representing features of Y as features of X, right? Okay, so there's a theory for that. This is in this paper in the AMS notices that I wrote a while ago. But then Erwin and Tomislav and people here actually found some applications for it. So clearly I don't have an application for the previous part of the talk yet, but maybe we will have some as we go. But they actually found two in the meantime in robotics. And so I was inspired to actually present what the theory is, because, it actually now is there. So take the set OM of all complex functions on the space of observables on M, and then ON is all the functions on the space of observables on the another space. N, a finite dimensional representation, is a double set of functions F and G. So these are the lifters on M, and these are the lifters on N. And then a representation, again, very similarly, is just your operator that, F, G, and F is just a mapping that says the lifters on G are some function F of the set of functions on M. So interestingly, there is a pullback composition operator that goes between these two spaces. And so you take the lifters, so G, you apply T to point M, and then you define that to be U on G of M. Isn't this interesting? It has some complexity to it, because the image of this set is the set of functions F that are constant on level sets of T, right? This doesn't make any sense. If you have level sets, so your T maps this whole circle into one point, then the function that you're defining must be constant on that circle. So that's a restriction. It's different. There is also the pseudo-inverse. So you start with some function F on M, you project to the space of functions that are constant on level sets of T, and then you identify this with the functions on N. And if you do that, then you define an operator P. And so that operator, so this is an interesting little proposition, under some technical conditions, the image of U, the operator that is equivalent to Koopman operator, is orthogonal to the subspace at the singular value of 0. So the spectral theory shows up again, right? But in the Koopman theory, you have the spectrum because you have an operator from space to itself. Here, you of course have maps between different spaces, and so it's the singular values that matter and not the eigenvalues. But this is a nice characterization because it basically says, all the functions that you can get out of this operator, that's orthogonal to singular value, and you can actually do some computations out of it. And this is a little more technical, but you can actually get that projection numerically from the data by averaging the value of your function F on the level sets of T. So you can get this out of data. All right. As I said, this actually does have some applications, and you can compute with our beloved formula that relies on the Moore-Penrose inverse again. So the computation itself is enabled. I think Erwin and Tomislav are going to talk about these methods later on. The last thing I want to show you is this is a very, very old work from about 98. This is actually the first paper in Koopman operator applications to real data systems. It's done in 98, 2000 CDC in Sydney, Australia, which was a very nice thing. And so we used it to parameter identification. But then with Will Redman, who is there, we started working on the idea that neural networks themselves have dynamical systems associated with them. And so the first thing that we did is on two different data sets, Will took the global magnitude pruning, which basically tells you I have a bunch of neurons, and I'm going to set to 0 the ones that have very little magnitude. And that was the adopted state of the art. And then he did the Koopman pruning, which is based on the eigenvalue 0 or eigenvalue 1 in discrete case, Koopman mode, and he got exactly the same curves. And so that means that the global magnitude pruning, which is a heuristic, is exactly a Koopman method for pruning neural networks. That was the beginning. We continued this by saying, okay, can we compare how neural network training goes in the various different cases? So we said, okay, if you have conjugacy between different systems, different trainings, that's something interesting and can be identified with the fact that the eigenvalues are the same. So here is the outcome. So here is the proof, well, at least numerically, Koopman proof, that online mirror descent and online gradient descent have the same eigenvalues, red and black, and the bisection method has very different eigenvalues. Koopman for algorithms is, I think, what Yanis introduced to start with, but we kind of followed up, and he's a co-author on this. And then you can take the Wasserstein distance between different sets in the eigenvalues in the complex plane and show that different widths of the neural network actually have, if you have a neural network with different widths, they will have different trainings, right? This is the difference between 10 and 40 width. And you can also show that the early stage training is quite different than the late stage training. This is the difference between them. If you're seeing yellow here, there is a relatively large difference between those stages of training. But most interestingly, Will was able to show that the phenomenon of grokking, which of course leads to things like generalization, this is the situation when in training you get pretty good results on the accuracy, but then on the test set, if you need to keep training for a long time before you get the same accuracy, they have the unconstrained situation where you have that grokking, so you're not constraining the norm of the inputs, is very different than the constrained situation in which you have no grokking, and you see the large difference between, for example, these two eigenvalues here and those over there. All right, so I tried to squeeze this into 25 minutes and I failed by a minute or two. But so there are three things that I said. The notion of function spaces in control theory is not something that we are currently completely clear on as a community. I think it's an interesting place where we need to do a lot more work so that we have the design procedures also with guarantees that our frameworks are precisely correct. So I'm hoping to see some work on that. I'm also hoping to see more static Koopman operator work, because it's an idea that transcends dynamical systems, I think. So it's these maps between different spaces can also be captured by these pullback type or composition type operators. And then finally, there is a lot of work. This is DeepMind, I think, over here. And then this Princeton Carnegie Mellon collaboration that speaks about using neural networks in conjunction with the Koopman operator theory. In this paper in particular by DeepMind, particularly trying to resurrect the recurrent neural networks by watching the eigenvalues of the Koopman operator and preventing the exploding or vanishing gradient problem that recurrent neural networks have. All right. Thank you for indulging for a few more minutes than I was allotted, but that's all I had.